So the last thing we talked about was inductive reasoning. Remember that? We look at a pattern and then we make a conjecture about what's going to happen next based on what we've seen in the past. Okay? So it could be something like, I look at, we started with this one. We did this thing. And I did the, and then I asked you guys, okay, what's going to happen next? And you all made a conjecture about what was going to happen next. And some of you were right. And some of you were not right. Right? And some of you thought I would just make 3 lines instead of 2 lines or 1 line. So I wanted you to understand that your conjecture is just an educated guess about what's going to happen next based on your observation. It doesn't mean that you're always right, okay? And when we see something where we're not right, what do we call that? What is that one thing we find that shows that we're not right? Remember the word for it? That's right, a counterexample, okay? So a counterexample. We may have something like the sum of any two the sum of any 2 even integers is even. Well, how did I come up with that conjecture? Well, I thought about it a few times. I just took 2 evens, added them, even. Took 2 different ones, added them, even. I took 0 and a negative even number, -4, added them together, even. So my conjecture is the sum of any 2 even numbers is even. Okay? Now, is that proof that that's true? No, that's not proof that it's true. It's just a conjecture about what I see. Okay? Today, we're going to talk about the law of detachment. So, deductive reasoning. So we're going to talk about the law of detachment and the law of syllogism. So the law of deductive reasoning, that's today's lesson. So will you turn to page 78? Okay. Deductive reasoning is very different from inductive reasoning, okay? With deductive reasoning, I don't just look at some examples and say, well, that looks like it's happening all the time. Deductive reasoning, what we do is we form a logical argument and show that it has to be working all the time, okay? So what we do is we take, what would we take? Facts, something you know for sure. Properties, the laws of logic, definitions, and we make a logical argument about it. Okay? Now let's do that even number thing again. The sum of any 2 even integers is even. Okay? Well, how do I write, and how can I write algebraically a number that I know is even? Well, 2n. Okay? What do I know about 2 times some number? It's even. Isn't that the definition of an even number? It's a multiple of 2. Can n be a positive or negative or 0 even? Yes. Okay? So it doesn't matter what integer n is, 2n is even. Right, West?
Yep.
Thought I was right. Okay, so I need some other even number. Don't have a lot of imagination, so I'm going to go with 2m. There's another even number, isn't it? Tatum? 2m has to be even, doesn't it? Okay, and what was my conjecture? That if I added them together, that sum would be even. Well, if I want to write this another way, there's a property of mathematics called the distributive property. And it says that 2n plus 2m is equal to 2 times the quantity n plus m. Okay? Now, if m and n are both integers, and I add them together and times the answer by 2, isn't that by definition even? Okay, this is the law, or this is deductive reasoning. I just made a logical argument to show for sure that the sum of any two even integers is even. Do you see how that's different from deductive reasoning? I'll take it by your dead silence that that's a yes. Some of you nodded your head a little. So inductive, look at a pattern, say, I think this happens because it seems to always happen, right? Or it just seems like it should happen next. Deductive reasoning, logical argument to show that it actually has to be true. Okay? I did another one with you earlier. We did the vertical angle theorem. A theorem is a logical argument that shows something must be true. So, I don't know why I numbered it 1, 3, 2. But anyway, I proved the vertical angle theorem. I proved that angle 1 and angle 2 were congruent, didn't I? We made that logical argument. I'm just going to go through it quickly. Inductive reasoning. They look like they should be the same. Look at them. Look at them. What if I make the angles a little more bigger here? They look the same, right? I measure them. Yeah, they seem to be the same. That's inductive reasoning. Now deductive reasoning. Aren't these two a linear pair? So wouldn't they be supplementary then? So their sum's 180. And aren't these two a linear pair? So they're supplementary. Their sum's 180. So if these two add up to 180 and these two add up to 180, wouldn't 1 and 2 have to be the same measure? Is there any other possibility then? So that is deductive reasoning. That's a logical argument that shows that it has to be true. I think if you guys remember, we said this. Since they're a linear pair, they're supplementary. Same reason. And then we said this. And then we subtracted, that's a property, subtraction property of equality. So we subtracted this from both sides, and we got the measure of angle 1 equals the measure of angle 2. And by the way, if two angles have the same measure, aren't they congruent? Isn't that the definition of congruent? Okay, so that's the logical argument that we have. So we have inductive reasoning, deductive reasoning. Do you understand the difference? Okay, all right. Now, we have to learn with deductive reasoning, we have to learn a couple of laws. The first one is the law of detachment. Okay, here's how it works. If P leads to Q, okay, now imagine some general case. If it's an acute angle, then its measure is between 0 and 90. Is that true? Thanks. Let's try that again. Is everyone with me here? If it's an acute angle, then its measure is between 0 and 90. Is that true? Yes. Now, I want you to notice that was kind of a general case. I didn't name a particular angle, did I? Okay? I just said if it's some acute angle, then its measure is between. Okay. So if that statement is true, now let's be specific now. Okay, here's this angle right here. angle A is an acute angle, what can we then conclude? This, yeah, I didn't even need to measure that, did I? It's measures between 0 and 90. So if this statement, if P leads to Q, if that's true, and P is true, that's an acute angle, then Q is true. It leads us to that. Now I want you to notice, really unspecific statement, if-then statement, right? If it's true, and then if I have this specific thing, this one's an acute angle, then we can conclude what? It's measures between 0 and 90 degrees. Now let's say if it's an acute angle, it's measures between 0 and 90. Okay, see this angle right here? Its angle is between 0 and 90 degrees. What can we then conclude? No! Does this have an arrow going both directions? Then don't go both directions. Now I know you think you can conclude it because it's true, right? It should work in your brain, right? I'm not disagreeing with that. What I'm saying is, according to the law of detachment, you can't do that. You can't start with the hypothesis and go back to the conclusion. Okay? So, let's think about some more of these for a minute. If two segments, okay, so if two segments are congruent, that's the hypothesis. Two segments are congruent, then their measures are equal. Is that true? Okay, that has to be true. That has to be true. Now, I tell you these two segments are congruent. What can you then conclude? That their measures are equal. Okay, so notice general case, if some two segments are congruent, then their measures are equal. Now let's be specific. Those two are congruent. Their measures are equal. You with me? Okay. If a dog is a Great Dane, then it's a big dog. Okay. Otis is a Great Dane. What can you conclude? He's a big dog. Okay, now, if a dog's a big Great Dane, it's a big dog. Okay. Rufus is a big dog. What can we conclude? Nothing. You can't conclude anything. You can't go back and conclude he's a Great Dane. He's a St. Bernard, people. You can't go, it's one directional. Now, I get it with this one because does that one work either way? Yeah, it does. But in the one I'm talking about, look at Rufus. Look at Rufus. Just because he's a Great Dane and a big dog, yeah. But now look at Otis. He's a big dog. He's a big dog. Does that mean he's a Great Dane? No, it's one directional. You can't start with the conclusion and go to the hypothesis. So, if you clean your room, then you can go to the movies. Macy. So, you hear Macy's mom say that. Okay? If you clean your room, then you can go to the movies. And you know, Macy's mom, she's a good mom. She doesn't mess around. She doesn't kid around. She makes you do it, right? So later on, you see Macy at the movies. Can you conclude she cleaned her room? No. See how it doesn't go back the other way? Now, later on you go over to Macy's house and her room's clean. What can you conclude? She can go to the movies. Okay? One directional. Are you getting it now? Do I need to do another one? If I roll a 6, then no homework.
Is this real? Please.
Dang right it's real. Oh. Oh!
Dang it!
5.
Close enough.
So.
There is a 6 on your dice.
Can't, so, if that one's not, okay, so, this is true statement. So, if, was this part of the real thing true? No. So then can we conclude no homework? We can't conclude that, okay? And then also, end of class, you guys are all walking out, and you have no homework. Can you conclude that I did not roll a 6 from that? No, I could have not given you homework because you're all nice. We know that's not happening, but that's possible, right? There's other reasons, okay? So don't go back, okay? So some of these are going to say, they're going to ask you, what can you conclude based off of this? If possible. There might be some where you have to say, I can't conclude anything. That doesn't follow the law of detachment. Okay? All right, now that was the easy one. That's right. I saw your eyes get big. That was the easy one. Here is the more difficult one. Sort of. Law of syllogism. Okay? It works like this. If A, then, I shouldn't put A, I should put P. If P, then Q. If Q, then R. If P, then R. Okay, so let's think about this for a minute. Let me think if I can think of a true one. If you clean your room, then you can go to the movies. Now this is important. Then you can go to the movies. Now watch. Go to the movies. If you go to the movies, do you see what I just did? See how I took the conclusion here and used it as the hypothesis here? If you go to the movies, then you get sick on popcorn. Let's say both those statements are true. And it has to work this way. You have to take the conclusion here and use it as a new hypothesis that leads us to a new conclusion. If I clean my room, then I can go to the movies. If I go to the movies, then I'm going to get sick on popcorn. So now, I clean my room. What's going to happen? I'm going to get sick on popcorn. That's how the law of syllogism works. Okay? Now remember, with the law of detachment, we had P leads to Q. That's a true statement, right? And then I give you a true hypothesis. It can lead to a true conclusion. With the law of syllogism, see how they give you two full if-then statements? Okay? And then you have to make a new if-then statement based off those two. And it gets a little iffy sometimes. Think of this one. I'm going to write it for you so we can see it in our mind a little bit. If it is a Great Dane, then it is a big dog. Okay, there's our first if-then statement. Now what has to happen in the second if-then statement? Tatum, you with me?
Yes.
I know you're back in the corner of death back there. Okay, the next one have to say, if what? Okay, it's a big dog. It is a big dog. Then what? Okay, good. Then it eats a lot. Okay. So now, does this seem to follow the law of syllogism? Hypothesis becomes the new, conclusion becomes the new hypothesis, leads us somewhere new, right? So now what can we say? If it's a Great Dane, then it eats a lot. That's how the law of syllogism works. Okay? Now, I want you to look at example 5A on page 78. And I just want you to study that one for a minute. And I want you to think about if that follows the law of syllogism, and if it does, what conclusion can you make? Are you confused? Anybody confused looking at the example 5A? Does that seem to follow the law of syllogism? You all have wrinkly foreheads. Why are your foreheads wrinkly? What's the matter? Isn't it working? West, is it not working? You think it is? Can you make a conclusion for me? So pretty good. Okay, I want you to look at this one now. If x is greater than 5, then x squared is greater than 25. Is that true? Okay. If x squared is greater than 25, you see what just happened right there? Everybody? Then x squared is greater than 20. Is that true? Isn't it? If x squared is greater than 25, then x squared... If something's greater than 25, isn't it greater than 20?
Yeah.
Yeah, I think that's true. If x is more than 5, then x squared's got to be more than 25. I think that's true. And if x squared's more than 25, then it's more than 20. I think that's true. And so I think we can say if x is greater than 5, then x squared is greater than 20. So see how I went from our first hypothesis to our last conclusion, didn't I? Now, isn't that exactly what it says on example 5A? Isn't it exactly the same? Why is 5A so hard and this one was easier? Why?
Because the conclusion on the first one is different than the hypothesis on the next.
Yeah, they just had them written in the opposite order, didn't they? Okay, and so you didn't see the conclusion here become the hypothesis here, because it was just the order that they wrote the if-then statements in. It doesn't matter what order they write them in; it can still work. So you have to think about it. Okay. Let's look at B. If a polygon is regular, then all the angles in the interior of the polygon are congruent. If a polygon is regular, wait a minute, didn't it just say that? Did they take the conclusion and make it the new hypothesis? No. Regular, then all its sides are congruent. Both those statements are true. But does it follow the law of syllogism? No. So can you make any other conclusions? No. That's it. That's how it works. You are all now smart. That's right. Here you go.